Hi, so this is again EEE153, week 6, lecture 3, which is on the analog input peripherals on modules for PIC32. So, what we will be covering here is that for the PIC32MX family, it's comparator and ADC modules, their features, SFRs, and some sample configuration. So first we have the PIC32MX comparator. So simply this, just a simple comparator, wherein we can select our input pins either as our C1 in minus or plus pins, reconfigurable pins, and we can also reverse or invert our output here. Then we also have the option of enabling the output of our comparator as an output pin, or we can just read it in our program or in the memory using these bits. So the comparator SFRs, we only have one control register. So we replace this X with either 1 or 2 if we want to use comparator 1 or 2. So we have a on bit that enables or disables our comparator, an output enable bit which enables or disables the external output. So enabling or disabling this bit doesn't necessarily mean that the comparator is will not output anything. It just means that our external output pin is disabled. Then we have the polarity select, wherein we can invert the output of our comparator. And then the cout bit, wherein we can check the status of the output of our comparator. So alternatively, we can use the cm stat bits or comparator status bits to check for the output. So we can either use C2 out for output of comparator 2 or C1 out for the output of comparator 1. Then here we have we can also set the polarity of the event we want our interrupt to represent. So if we set this as 0, no interrupts will be generated by the comparator. If we set it to 0, 1, every low to high transition of the comparator will trigger an interrupt. If we set it at 1 to 0, each high to low transition will generate an interrupt. And lastly, setting it as 1, 1 will make any transition in the comparator input generate an interrupt. So next is the basically input select bits, cref, that you choose which positive input you want. It can either be a internal comparator voltage reference or our C1 in plus pin. Next is for the negative channel of the comparator, we can select an internal voltage reference, the input pin of our other comparator, which is C2. Also, inversely, if this is for the SFR of comparator 2, this will say comparator 1. And then you can also choose the actual C1 input pins. And lastly, the SFRs, the interrupt SFRs. So interrupt flag is in IFS1, enable interrupt is in IEC1, and the interrupt priority is in IPC7. So as a simple example, here we have a sample code, and configuring the C2 out and the C2 in pin is left as an exercise to the student. So here we just enable the output interrupt on C2 out. We use IV ref as our voltage reference and use C2 in as our positive input. So note that we are using comparator 2. Then lastly, when we are ready, we turn on the comparator. So what this does is whenever we see that the comparator output is high, we turn an LED on, or else turn an LED off, or whatever event you want. So now on to the more uh, bigger module is the ADC. So the PIC32 has a single 10-bit SAR ADC. And even if it's just one, we can connect it to any of the 16 analog inputs. And it also has a mode that can periodically sweep and convert all of these inputs or a subset of those 16 analog inputs. Then we also have a selectable conversion trigger source, which means our ADC can sample automatically by itself or through an external event. Then next is we have 8 different conversion formats. Since our output is just 10 bits, depending on your need, there might be a format that suits you better. Then we have our ADC has a buffer that can store up to 16 results at a time. And then our ADC has a minimum of 1 microsecond per sample and conversion, which means that our ADC can sample up to almost 1 megahertz. But usually we don't go that fast uh, in order to ensure proper operation. So yes, this is a simplified schematic of the ADC module of the PIC32. So let's highlight a few parts first. So this is our successive approximation analog to digital converter, or basically the successive approximation register, which the SAR is named for. So this comes with the logic of the successive approximation, or the binary search algorithm for SAR. So up here on top, we have the reference select multiplexers. So we can either use an external VREF or our analog VDD and analog VSS pin of our microcontroller. So we can select this by changing the value of our voltage reference configuration bits, or VCFG. And given in this table, you know which voltage reference you're using depending on its value. So next we have here the sample and hold circuit, which comes with some amplification with the differencing amplifier. So uh, here for the sampling part, we are just using a switch. So of course, it will not be a mechanical switch. This is an electrical switch inside the PIC32. And then we have a capacitor here to hold the sampled voltage for the SAR ADC to make comparisons with. Next here is we have the negative input selection. So the negative input of the differencing amp of our sample and hold circuit. So usually you will be just using the ref L or the negative voltage reference of our SAR ADC, but sometimes you can also use our analog input 1 pin, or AN1. Now this here is our negative input select bit for multiplexer A setting for CH0 and A, and a multiplexer B select bit for CH0 and B. So why do we have two of these? So basically they just determine which channel we are actually using, and we have a MUX A and a MUX B setting because our ADC has the alternating input sample mode select. So when we set this as 0, our ADC just always follows this one. But if we enable the alternate input sample mode, for the first conversion, we will be using the MUX A setting, and for the next conversion, we will be using the MUX B setting, and so on and so forth. Now, the same is true for our positive input, but this time we can select any of our analog input pins from AN0 to AN15. So that is what we set with CH0SB, or select B and select A for multiplexer A and multiplexer B setting. Our channel select A is multiplex also with the channel scan bit. So when we enable channel scan, this means uh, our input will be scanned from 0 to 15. So the first conversion will be the converted value from a and 0. The next one will be for a and 1, and so on and so forth. And then you can choose to skip some of the pins by setting the values for our CSSL register. Then lastly, we have the data buffer for the ADC. So our data buffer has two modes. So we can choose to use two 8-word buffers or as one 16-word buffer. So we usually want to use buffer mode 1 whenever our ADC is slowly sampling our input. Because in this configuration, when we are reading ADC1 buff 7 to 0, our ADC will be filling up or populating with samples ADC buffer 15 to 8. And when we want to read ADC buffer 15 to 8, our ADC is storing its information in buffers 7 to 0. And lastly, these are the data output format bits. Usually, we're just going to use 000, the integer 16-bit integer format. But depending on your situation, you can use a 32-bit format or a signed format or a fractional format. So that's the simplified schematic of the ADC module. So now I'm just gonna enumerate the special function registers of the ADC. So we have three. So the first one, the first control register, usually is concerned with the mode of operation of the ADC. So we have the on bit, as with any other module, the form bits, and the auto sample enable or disable bit. We set this bit whenever we want our ADC to start sampling automatically. Then we have this clear ASAM bit, which when we set it to 1, whenever there is an interrupt of the ADC, the ASAM bit will be automatically be cleared, which means every time the ADC is interrupted, auto sampling is disabled. The next, if we don't want to use our ADC in auto sampling mode, we use the samp bit to either set it to enable sampling and then clear it to enable the conversion. Then we can also check the done bit in order to make sure our ADC has finished converting. More with our control register 1 is the SSRC bits or the trigger source select bits. Usually we're just using this first one to auto convert, and then if we want to manually convert by setting the samp bit, we use we set it as 000. Next is our control register 2, which is concerned with the sampling mode of our ADC. So the first bits are the voltage configuration reference, which I think I showed a while ago. Then the channel select, scan, enable, or disable, the buffering mode, and the alternate input mode, enable or disable. Also with control register 2 is the SMPI or the conversion sequences per interrupt selection. So we can configure our ADC to generate an interrupt after every conversion or after every 16th conversion. So depending on whichever you want to use. Then we also have a buffer status fill bit. So when we use buffer mode 1 or when we use two 8-word buffers, it tells us which of the buffers are currently being filled and which buffers should we be accessing. Then next is our control register 3, which is concerned with the timing and clock of our ADC. So the first bit here, ADRC, selects if we want to use the internal RC clock of the ADC or if we want to use the external peripheral bus clock. Now, when we are using the external peripheral bus clock, we also have the option to select our prescaler because we are never quite sure if our peripheral bus clock might be too fast for our ADC. Then this SAMC bits or the auto sample time bits just say how long our sampling circuit samples our input before a conversion is started whenever we are in auto sample mode. So when we set, it's not allowed to set it at 0 because you cannot sample anything in 0 seconds. So at least it should be set to at least 1 or to the minimum. And speaking of minimum conversion times, so we should note that each conversion needs at least 12 clock periods of our ADC. So that is 10 of these are for the conversion, and then 2 of these is for writing the data in our buffers. And then our ADC clock period must be at least 65 nanoseconds, and our minimum sample time is 132 nanoseconds. So we need to take note of these. So for when example, we have a peripheral bus clock of 80 megahertz, what should we set as values for our ADCS and SA and C? And those are the control registers. Now here are some other registers that concern the ADC. So first is the channel select register or AD1CHS, which is where our which is where we set the channel inputs for our MUX B or MUX A setting for our negative or positive input. Next is the pin configuration register, which you should be familiar with right now since this is what you will be using when you are configuring digital input pins. Then next is the CSSL or channel scan register, wherein we specify which channels we are including or excluding when we want to use the ADC in channel scan mode. And then lastly, these are the interrupt registers associated with the ADC. So the interrupt flag and interrupt enable is in the IFS1 and IEC1. And our interrupt priority is in IPC6. Now, those are a lot of registers. In order to have a simple example, we have the 7 steps for configuration in auto sampling mode. So first, you would want to configure your input pins using the PCFG register. Next is you specify which inputs you are using with AD1CHS. Or if you are also in channel select mode, you also configure AD1CSSL. Next is you select your sampling trigger and the form you want your output to be. So that is SSRC and form. Next is you will want to set your voltage reference through VCFG and the number of conversions per interrupt SMPI if you plan to use interrupts. And then since these are also in AD1Con2, you can also select which buffer mode you want and enable scan mode if you want it. Next is you configure your clock source, sampling time, and ADC clock period with AD1Con3. Lastly, you configure your interrupt if you are going to need them before turning your ADC on. So as a simple example, we have a sample code here. So first is we set RB2 or AN2 as an analog input pin. Then we select AN2 in channel select A, and we set VR minus as our negative input. Then we set SSRC to auto convert our to set our ADC to auto convert mode and use the 16-bit integer form. And then we use the analog VDD and analog VSS for our reference. And then we set it we set our ADC to generate an interrupt after every 4 conversions. So actually, this should be 3. Then next is we use the peripheral bus clock by setting ADRC to 0, and we sample every 4 time periods. So that means our every sample is our hold capacitor is charged for 4 clock periods before we start conversion. And then lastly, we configure our prescaler to be so that our A to D clock is 8 times that of the peripheral bus clock. Then we clear the interrupt flag, set the priority, and enable the interrupt. Lastly, we turn the AD1 or ADC on. And since we are in auto sampling mode, we have to set ASAM1 as ASAN to 1 in order for the automatic sampling and conversion to occur. Now this is a sample ISR for our ADC. So you see here we are using the ADC vector and using software context save. So since we did not set clear ASM in our configuration, we have to clear it manually. If that is, since I don't want my ADC to sample while I am in the interrupt service routine. Now, that's not really required, but it's really a matter of preference. Next, you can store your ADC values by directly accessing them to ADC1 buff 0 to ADC1 buff 3. Since we are we expect this interrupt after every 4 conversions. Then we can do other stuff with these values we've read before we start auto-sampling again and clear the interrupt flag before exiting the ISR. So in summary, I've just shown to you the PIC32MX analog input peripherals and how you can configure them. Then, especially for the ADC, it has many operating modes, so we just tackled the auto-sampling mode actually. And the other modes, well, they aren't, depending on your application, you may need to read up on them. Then lastly, if you want to maximize your ADC, if you want to sample at the fastest possible rate, you need to know your device timing specifications. So that's it for this lecture video. Thank you and have a good day.